Good morning. This is Gina Anderson from NASA's Office of Communications. Thank you for joining us today to talk with NASA officials to discuss the latest development in the Solar Electric Propulsion Project. The contract for the design and development of an advanced electric propulsion system that can significantly advance our nation's commercial space capabilities and enable deep space exploration missions and NASA's journey to Mars has been awarded to Aerojet Rocketdyne. Development of this technology will advance future in-space transportation capability for a variety of deep space human and robotic exploration missions, such as NASA's Asteroid Redirect Mission, or ARM, as well as private commercial space missions. Here to discuss the development of the Solar Electric Propulsion Project are Mr. Stephen Jurczyk, the Associate Administrator of NASA's Space Technology Mission Directorate here in Washington, and Mr. Bryan Smith, the Director of the Space Flight Systems Directorate at NASA's Glenn Research Center in Cleveland. Each speaker will provide a brief overview of the award and how development of this technology can advance future in-space transportation capabilities, and then we will open up the lines for questions. Your phones are on mute now. To get into the question queue, please press star 1 on your phone. The operator will call on you and open your mic during the question and answer section. Please stick to one question and identify to whom it is directed. We'll have about 30 minutes for questions, and we want to ensure we accommodate for each of our speakers. First, we will hear from Mr. Steve Jurczyk and what this new development means to our journey to Mars and ARM.
Hey, good morning, everybody. So a little bit about my organization and what we do for the agency first. So we are the Space Technology Mission Directorate, and we develop what's known as cross-cutting technologies for the agency to enable both robotic and human exploration of the solar system. So there are space technologies developed in Human Exploration Operations Mission Directorate, focused on solely on human exploration. Same thing in the Science Mission Directorate in astrophysics, earth science, heliophysics, and planetary science, focused on their missions. We're developing technologies that apply to both what science wants to do and what we want to do with human exploration of the solar system, as well as have application to missions for other government agencies and capabilities they need, and commercial and the commercial space enterprise in the country. So solar electric, high power solar electric propulsion is a perfect example of a cross-cutting technology. We've done missions using lower power solar electric propulsion, for its high efficiency, what we call high ISP, but also known as gas mileage, very good gas mileage. So we can develop smaller spacecraft and that can be propelled by solar propulsion versus chemical propulsion. But the advance here is the higher power and thus the higher thrust. So again, it's going to be, our plan right now is to flight test the high power solar electric propulsion that Aerojet Rocketdyne, components and system that Aerojet Rocketdyne will be developing for us on the Asteroid Redirect Robotic mission, which is going to go out to an asteroid with a robotic system, grab a boulder off of an asteroid, and bring it back to a lunar orbit. And then there's a crewed part of that mission where we launch crew using SLS and Orion, and they rendezvous, explore the asteroid, bring samples back in lunar orbit. But it also is a critical capability for enabling human missions to Mars with respect to delivering cargo that we're going to have to deliver to the surface of Mars to allow people to live and work on the surface. And it also could be used in a combined system on a spacecraft, a combined chemical solar electric propulsion system to actually propel humans to Mars. It also can be used for science missions. An example would be a round-trip robotic science mission to bring samples back from Mars. So Mars Sample Return Mission, the spacecraft that goes to Mars, goes into orbit, releases a vehicle to the surface, and brings the samples back to that vehicle. Could go get there and come back using solar electric propulsion. And then other agencies would like it for its efficiency and operational flexibility. And then commercial companies also would love to have this capability for example, companies are looking at quote-unquote all-electric commercial communication satellites to get, and they've been using electrical propulsion for station keeping in geostationary orbit for years, but this would allow them to more rapidly get systems from geostationary transfer orbit to geo orbit for comm capability, or get larger systems from geostationary transfer orbit to geo. So just some of the applications of this high power STEP technology. I'm going to stop there and turn it over to Bryan Smith, who's going to talk a little bit more about the specifics of the tech and also what Aerojet Rocketdyne is going to be doing for us.
Thank you, Steve. This is Bryan Smith at the Glenn Research Center in Cleveland, Ohio. We are very excited to be working with this contract. The technology itself, as Dr. Jurczyk has alluded to, is very significant. And a little history here as well. Glenn Research Center, which was previously the Lewis Research Center, has been working on this technology actually since the 50s. And it's fascinating to track the original ideas and actually how it's been adopted over the years. And as was mentioned earlier, the infusion of this technology into the commercial satellite industry has taken place over the years and has displaced a lot of the propellant that the commercial satellites used to have to take up in order to do their station keeping operations. And by displacing that propellant, you can either use the additional mass for additional revenue-generating transponders, or you could have a longer life, which both turns into certainly a better revenue stream for a lot of operators. So we've watched that take place over the years. And then another sort of on-ramping of electrical propulsion came for deep space applications, and we've seen some excellent examples of that through the Dawn mission recently that went to Ceres and Vesta asteroids. So that particular application was taking advantage of that high efficiency that these engines generate. So now we're basically moving into almost like another greater application where we've really looked at this in terms of orbital transfer. How much can you add to the normal, say, let's just call it the rocket equation, where you want to use propellant in the most efficient way to do deep space operations. And so what this technology moves us to in this device is a capability over 2 times greater than is presently being flown today. And so taking those strings of engines, and one of these would comprise a string, and putting a few of those together, now we move to a level of approximately 50 kilowatts of electrical propulsion capability. And with that, you then can do significant orbital transfer operations. And that's where we really begin to see moving of the assets into deep space, and really it becomes that next step in deep space exploration that we were trying to do. A little bit more about the contract itself. It's a 36-month period of performance. We will do a base part of this contract that looks at the development units, the qualification units, goes through a critical design review, and then hopefully we'll exercise the option of then buying multiple units that then we can apply hopefully to the ARM mission. I think probably my top level summary. I guess another way to look at this too, we've looked at it as a important part of a drivetrain, if you can think of it that way. I know our neighbors here in Detroit get excited every time they put together a new platform for a new pickup truck or a new engine system, and that's basically what this is. If you look at the arrays, the high-power arrays that the Space Technology Mission Directorate has developed, and you couple that with this, I call it new engine system, we basically are building a new drivetrain that enables whole new platforms for deep space exploration. So I think that's how I look at it as well. So with that, if there's any questions, I guess we were going to go to that.
Thank you, Bryan. We'll now open up the call for questions. We've got 1 on the line, 2 on the line. The instructions again are to get into the question queue, please press *1 on your phone. The operator will call on you and open your mic during the question and answer session. So with that, our first question will come from Mr. Eric Berger from Ars Technica.
Actually, we have Leonard David on the line.
Yeah, hi. Can you hear me okay?
Loud and clear.
Okay. Maybe for Bryan, I interested in, I'm getting old, but I remember when they clustered Saturn engines together, there was a big worry about how these things gang together. Any concern about when you put multiple engines together like that? Is there any interaction between them? Is that part of the study that Aerojet would do?
Yes, there's always concern when you put devices next to each other. We have done tests here at Glenn in our facilities of putting the actual engines next to each other, and we've been able to mitigate any effects that would be negative on those systems. Additionally, for these types of systems, we make sure that there's no deleterious effect on the spacecraft itself through the operation of these engines. So we'd study the plume field as well, which, as you can imagine, operates a little differently than classic chemical systems.
Yeah. Also, we for the Asteroid Redirect Robotic Mission, which is being led by JPL, they have study contracts out for spacecraft to accommodate the solar, the large solar arrays and the multiple strings of electric propulsion thrusters. And so, that's part of the ongoing, spacecraft accommodation study. And Glenn Research Center is significantly involved in that to make sure that we don't have any adverse performance by putting multiple strings of thruster elements on the spacecraft for ARM.
Great, thanks.
Thank you, Eric Berger. You may ask a question.
Okay. Good morning, guys. Thanks for doing this. I'm curious about the capability of this system. You talked about stringing them together, and I'm curious. I think you said it was a 50 kilowatt power system. How long would it take for that to deliver cargo to Mars? Do you think? And then how does this contract fit within the recent next step contract to say Vasimir and NASA's overall plans for developing electric propulsion?
So I guess I'll start with the first part of the question. And the way to think of it, I think, is our building blocks. And so you have to the way we've tried to do this is decompose it to not jump off and to make a giant thruster right away, because then you're stuck with something that might be oversized. So we were trying to pick the right size thruster that allowed us to do a significant delta from what's being flown today. So, for example, today's operational level is 4.5 kilowatts of this type of device. So we moved purposely to 12.5 kilowatts. So it's an achievable level that we can do. Also, you don't always have to put these together. You can use them. You could use just a single string if you wanted for a particular mission. Control entities may want to use just a single string, for example. So this allowed that building block approach, and it also fit in what we believed was our next increment, and the ARM mission is an example of that. That's a 50 kilowatt class mission, building block fashion. Similar, I would think, if you had to go to Vasimir, that's just a larger extension farther out in time of higher power systems. So this was just chosen sort of on that pathway.
Yeah. So that's basically it. This is more of so what we're doing with the magnetically shielded Hall thruster technology is more of an evolution of the previous electric propulsion technology. So it's like Bryan said, it's the next step. Moving to the higher power electric propulsion, 100 kilowatts in a single engine. That's a much bigger leap in technology. And then Vasimir is a completely different technology where you're using electromagnetic waves to ionize a gas and then accelerate it using magnetic fields to get higher power and higher thrust. So So if we were successful in VASME or other higher power technologies, that could be a solution, particularly for more rapid transit of cargo or even crew. But that's technologically at a lower readiness level and farther out. With respect to your question on how long it would take to get to Mars, I guess this is not a great answer, but it depends, right? It depends on the orbital mechanics and when you're going, the size of the spacecraft, what trajectories you're able to take, et cetera. But we with a chemical propulsion system, we can get for favorable launch opportunity to Mars that happens every 26 months. We get to Mars nominally in 8 or 9 months with chemical propulsion. So solar electric is much lower thrust, so it would take you quite a bit longer than 8 or 9 months.
Thank you. Bill Harwood, you may ask a question.
Yeah, hi, Bill Harwood, CBS News. Just to follow up on Brian's question, what is quite a bit longer for for the class of spacecraft we're currently sending to Mars? And I'm not talking about habitats and human beings, but I'll just for argument's sake, a 1-ton spacecraft like Mars 2020 or Curiosity. Let me ask that first. I'm just trying to get a sense of how it compares mission duration time to chemical propulsion at that scale.
Yeah, so Bryan, can you basically maybe we can answer that by just delta in thrust from current chemical systems to what we're talking about, 50 kilowatt SEP system.
Yeah, again, you're back to it depends on your initial launch chemical that you use to insert it. So it depends how you parse the mission. So if you rely more on chemical initially, of course you're going to get there faster. If you step down to one of the advantages, you can step down to a lower performing launch vehicle, which would save you resources, and then you just have to make up that time on the other end. But you're still working within that range of 24, 36 months max of these types of missions, depending on how far you step down your chemical system and rely on your SEP system to make up that difference.
Yeah. So there's another trade too. You can stay on the larger launch vehicle, but your spacecraft is going to weigh less because the SEP is more volumetrically efficient, better gas mileage. So there's a trade there too that you could make what you lose in thrust in the in-space propulsion system you could make up in Earth escape velocity. So it's not an easy question to answer. However, I will tell you this: in the bigger picture, we're in this type of SEP system. We would plan on using it to send robotic spacecraft and cargo to Mars. Now, there's going to be a pretty long logistics train for human space flight. There's lots of things we're going to have to get there and put on the surface before we ever send crew. And so as long as we plan that out, then, we have the time using SLS. We'll have the capability and time to, use SEP to get the cargo there, get it in place on the surface before sending crew.
Yeah, this is Bryan again. I think the real takeaway for it is that it gives you that option space where chemical is restrictive in its orbital mechanics. The SCP systems, solar electric propulsion systems, allow you those trades and allow you to either step down in launch vehicle class or increase cargo.
Thank you. Mike Wall, you may ask a question.
Thank you, guys. I just had a quick question about the timing. Could you just kind of walk me through? I mean, this is a 36-month contract, so you're expecting to actually get something that's been fully tested and validated at the end of 36 months. And if everything looks good, then you'll sign another contract for 4 flight units. I mean, is that how it works?
No, actually, there's the base period is less than the 36 months, and then the base period takes it through. I have the exact date in front of me, but it's a period less than 36 months.
It goes to CDR.
Goes to CDR
and then
about 2 years.
About
right. A little short of 2 years is the base period, and then a delivery period would extend through the 36 months.
Thank you. Alan Boyle, you may ask a question.
Yes, thank you. I wanted to ask about the timing for the asteroid redirect mission. it seems like that's kind of a very definite schedule, and so if you could describe when the launch is going to be, I really think that you have to kind of lay those plans in terms of what the launch and the transit time is going to be. So I imagine with SEP, it's going to take a relatively long time compared with chemical rockets. So if you could lay out that schedule, that would be great. And then I guess another quick point would be on the commercialization of the technology, whether people would be paying to license the technology from Aerojet or whether NASA is making this freely available to other commercial engine builders. Thanks.
Okay, so this is Steve Jurczyk. I'm going to answer the second question first, and Bryan, feel free to add. Obviously the technology, we embarked on a multi-year technology development and test activity at Glenn Research Center, and all of that, we've made all of that design data and test data available already to industry. And it was up to them whether how much they wanted to leverage that, and so that'll continue to be the case. Anything we do now, I think the plans for Aerojet Rocketdyne are to productize what they develop for us, and then sell it as a propulsion system option for spacecraft developers and spacecraft systems integrators, for NASA missions, other missions for other government agencies, or missions for commercial applications like commercial comm. So that's the answer to the answer to the second part of that question, Steve again. So the answer to the first one is yes. So we are still in pre-formulation for the asteroid redirect mission, both the robotics part and the human part. And so we are like I said, we're doing spacecraft study contracts, along with developing the electropropulsion technology that is going to enable the mission. Nominally, we were looking at launching in the 2020, 2021 time frame, right? And we would go and grab a big boulder off an asteroid and bring it back in the 2025, 26 time frame, in which we launch a crew, or we're still using Orion and SLS, launch crew to lunar orbit. So that's what it also depends on the target asteroid, right? We have not selected a target asteroid. We're continually using ground-based assets to find new asteroids and then characterize asteroids that we know about and any new ones that we find. That's out of the Science Mission Directorate. Lindley Johnson, who's just been recently named the Planetary Protection Officer for NASA, and he has the asteroid program. And so the Science Mission Director will continue to find and characterize asteroids, and as we get closer to the actually doing the detailed design for the mission, we'll pick a target, and then that'll drive the detailed timing of when we launch, when we get there, and when we come back and put the boulder in lunar orbit.
Thank you. Ken Kramer of Universe Today. You may ask your question.
Hi, thanks for taking my question. What I'm wondering is, first, can you talk about a little bit about the size and the gas that this thruster is going to use, and talk a little bit more too about with this whole thruster that you have already developed. What exactly is it that you want Aerojet Rocketdyne to do beyond what NASA has already done? Thanks.
This is Bryan.
Okay. Yeah.
I think what we have done at NASA is try to, as we do in many cases, try to drive out the technology itself for feasibility. So we were able to produce a device that could operate at these levels. Other key characteristics we were looking for was the ability to do something called magnetic shielding, for example. And the purpose of that was allow for a long life thruster operation. So there were a number of other attributes that we were trying to prove out in what were our developmental units. So thermal problems, again, balancing of the erosion mechanisms, looking for things that would make sure that we could get longer life. Again, feasibility. These were developmental units that NASA has been working with. So once we were comfortable with the feasibility and the ability to do this, that's where we would like to transfer this information, technology, and know-how into what would essentially be a production article. And so that's basically what this contract is doing.
Hey, this is Steve Jurczyk. I'd just like to add something that was part of the overall electric propulsion development, technology development effort, but not necessarily part of what we're doing at Aerojet Rocketdyne, and that is we work with two companies. We also need to generate more electrical power for the 50 kilowatt system, right? And so we let two contracts, led out of Glenn Research Center, we let two contracts, one with Orbital ATK and one with DSS, both in California, and they developed very innovative, large deployable solar array concepts and technologies. They developed ground prototypes and tested them so that they package up. They're very volumetrically efficient. They fold up and package up in a very small volume in the launch vehicle fairing, but they deploy to a large area with solar cells on them and they get the electrical power. One of the companies, DSS, actually has an agreement with Space Systems Aral to provide those arrays for commercial communication satellites that need that higher power. And then Orbital ATK flew their version, the Megaflex solar arrays, on one of the Cygnus spacecraft for our International Space Station cargo resupply mission. So that's another part of the overall electrical propulsion technology development that we're, worked with industry to develop the technology and also transferring the technology for other applications that's key to the high-power solar electrical propulsion.
Thank you. Again, if you'd like to ask a question, please press star followed by 1 on your touch-tone phone. Our next question comes from Leonard David of the Inside Outer Space. Your line is open.
Yeah, hi. Thanks again. I think, Bryan, you touched on it a little bit, but I'm curious about the technology. You mentioned decades of, evolution of these thrusters, and is there any? I know erosion is a big issue and clogging and things like that, and there's been a lot of new materials. Is that part of the plan to look at new materials for these thrusters? And maybe for Steve, just a quick follow-up on, you mentioned Mars sample return. I think they were talking about a new Mars orbiter to support humans on Mars activities and planning that could have SAP.
So this is Bryan. I'll try to address some of the technology that you asked for. Absolutely. I mean, we've looked at these thrusters, and again, the history is fascinating. The different materials that were used as propellants. In the early days, they looked at materials such as cesium and mercury as propellants. So we've moved to xenon for a number of reasons, and with that, you have to have the attendant concerns in working with xenon, but also the materials and erosion mechanisms themselves. We've studied those, and so we have looked at new materials for that. But also, as I mentioned earlier, working with this type of device, if you're able to set up an effective magnetic field, you limit the erosion mechanism, which is very key. And so all of those combine together, and you're working in a fairly compact device, so you have thermal issues also to worry about. We've tried to balance all of those to the best that we can, again, proving out that feasibility for this class of device. And again, it's different if you work to a gridded ion system, which is a different technology, that imposes a whole other set of challenges. So each of these types of electric propulsion devices at the different class levels and different application levels certainly have their own challenges.
Hey, and this is Steve Jurczyk. So we did get some funding this year to do very early pre-formulation study on a Mars 2022 mission. So right now, Mars 20, we're going to land a rover very, very similar to Curiosity with a different set of science instruments that launches in 2020, but we don't have a mission plan yet for 2022. So one of the missions we're considering for 2022 is what we're calling a Mars Telecom Orbiter. okay, that would just do that, because the orbital, we use orbital assets at Mars for telecom relay from the surface, and they're getting a little long in the tooth, getting a little old, the current assets around orbiting Mars. And so we're looking at a Mars Telecom Orbiter, and we're looking at a couple that the Science Mission Directorate is studying, and we're looking at a couple of technologies for that mission. One is high-power solar electric propulsion, which will get us there, as well as give some operational flexibility at Mars. We're also looking at deep space optical communications technology. Could we either augment an RF system or use optical communications, which is higher bandwidth, factor of 10 higher bandwidth than RF, for that potential telecom orbiter for a Mars 2022 mission.
Thank you. There are no more questions in the queue. I can turn it back over to Gina.
That's all the time we have for questions today. Thank you all for joining us. You can listen to a replay of this teleconference by dialing 1-800-925-2063. The password is 9715. This teleconference replay will be available 1 hour from now. The service will be available through May 21st. Thank you. If you have any additional questions for our participants today, please reach out to me at this is Gina, 202-358-1160, or email me at gina.n.anderson@nasa.gov. We'll do our best to accommodate all requests. Thank you, and have a